Welcome to Deep Science Sleep. Today, we talk soothing facts about our solar system sleep science. Opening, a calming night's journey. Close your eyes for a moment and imagine yourself floating. Not falling, but gently drifting through the softest darkness you've ever known. The weight of the day dissolves from your shoulders. Your breathing slows to match the ancient rhythms of the cosmos, and you find yourself suspended in the most peaceful place imaginable, the quiet vastness of space itself. Tonight, we're going on a journey together, but not the kind that requires any effort from you. No, this is a journey where you simply allow yourself to be carried along, like a leaf floating downstream on the gentlest current. We're going to explore our solar system, this magnificent neighborhood of worlds that spins through space with such grace and constancy that it becomes a lullaby in itself. Each planet, each moon, each gentle force that holds everything in its place. All of it moves to a rhythm that has continued for billions of years and will continue for billions more, offering us the most soothing reminder that some things in this universe are wonderfully, peacefully constant. Let yourself sink deeper into comfort now. Feel the softness beneath you, the quiet darkness behind your eyelids, and know that for the next while, there is nothing you need to do except listen and drift. The solar system awaits, patient and eternal, ready to share its gentlest secrets with you. The sun, our gentle stellar companion. At the heart of our solar system sits a star, our sun. And while we often think of it as a blazing inferno of incomprehensible power, there is something deeply calming about understanding its true nature. The sun is not a violent explosion, but rather a slow, steady dance of fusion that has been going on for 4.5 billion years and will continue for billions more. This is the cosmic equivalent of a campfire that never goes out, a hearth around which all the planets gather in their endless, graceful waltz. The sun produces its energy through a process so gradual, so patient, that it takes a single photon of light more than 100,000 years to travel from the core where it's created to the surface where it can finally escape into space. Imagine that journey. A particle of light, born in the unimaginable heat at the center of the sun, slowly bouncing its way outward through layer after layer of dense plasma, taking tens of thousands of human lifetimes just to reach the surface. And then, once it finally emerges, it takes only 8 minutes and 20 seconds to cross the 93 million miles between the sun and Earth, arriving here to warm your face on a spring morning or paint the sky gold at sunset. This patient journey speaks to the sun's fundamental stability. Unlike the dramatic explosions we might imagine, the sun burns its fuel with remarkable steadiness. It follows an 11-year cycle of activity, known as the solar cycle, where it transitions from periods of minimum activity to maximum and back again. During solar minimum, the sun's face is often completely smooth and spotless, like a perfect sphere of gold hanging in space. The sun's surface becomes a canvas of tranquility, with only the gentle churning of convection cells moving beneath the photosphere, invisible to our eyes but constant in their rhythm. As the cycle progresses towards solar maximum, dark spots begin to appear on the sun's surface. Sunspots, regions where the magnetic field is particularly strong and prevents some of the heat from the interior from reaching the surface. These spots are actually cooler than their surroundings, a relatively frigid 6,500 degrees Fahrenheit compared to the 10,000 degrees around them. During solar maximum, there might be dozens or even hundreds of these spots visible at once, creating patterns that flow and shift with the sun's 25-day rotation. But even at its most active, the sun maintains a beautiful order. The magnetic field that creates the sunspots follows predictable patterns. During each solar cycle, the sun's magnetic poles flip, with north becoming south and south becoming north, in a stately process that takes about 11 years to complete. After 2 complete cycles, spanning 22 years, the sun's magnetic field returns to its original configuration. This is called the Hale cycle, and it represents a deeper rhythm beneath the more familiar 11-year pattern. The solar cycle doesn't just affect the sun itself. It orchestrates a gentle symphony throughout the entire solar system. During periods of higher activity, the sun releases more solar wind, a constant stream of charged particles that flows outward in all directions at speeds of over 1 million miles per hour. This might sound violent, but the solar wind is actually quite sparse, with only a few particles per cubic inch even at Earth's distance. It's less like a gale and more like the lightest breath imaginable, sustained constantly across the vast distances of space. When these particles from the sun encounter Earth's magnetic field, they are guided along the field lines toward the poles, where they interact with atoms and molecules in our upper atmosphere to create the auroras, the northern and southern lights. These shimmering curtains of green, red, and purple light are the sun's gentle way of saying hello, a visual reminder of the invisible connections that bind all the objects in our solar system together. The sun's protective influence extends far beyond the auroras. Its magnetic field, carried outward by the solar wind, creates a bubble called the heliosphere that extends well past the orbit of Pluto. This invisible shield helps protect the planets from the harsh cosmic rays that permeate the galaxy, charged particles moving at nearly the speed of light that were accelerated by distant stellar explosions millions or billions of years ago. The heliosphere gently deflects many of these particles, creating a safer space for the planets within. It's like the sun wraps the entire solar system in an invisible blanket, offering protection from the cold vastness beyond. The sun's gravitational embrace is equally gentle and profound. Every object in the solar system, from the tiniest grain of dust to the massive gas giant Jupiter, is held in place by the sun's gravity. But this isn't a tight grip. It's more like a patient anchor, allowing each planet to follow its own elliptical path at its own pace. The sun contains 99.8% of all the mass in the solar system, which means its gravitational influence dominates everything, yet it allows complete freedom of movement within the elegant rules of orbital mechanics. Think of how the sun rises and sets with such predictability that ancient peoples could build entire calendars around it. How its light arrives each morning without fail. How its warmth creates the seasons in their eternal cycle. The sun is the definition of reliability, and there's something profoundly soothing about that constancy. In a universe full of chaotic events, violent collisions, and unpredictable phenomena, our sun is a beacon of stability. The sun's core burns through 600 million tons of hydrogen every single second, fusing it into helium and releasing the energy that makes life possible on Earth. Yet despite this enormous rate of consumption, the sun has enough fuel to continue shining steadily for another 5 billion years. 5 billion years of mornings, 5 billion years of sunsets, 5 billion years of gentle, unwavering light. It's a reminder that on cosmic timescales, our star is in no hurry at all. As you drift toward sleep, imagine the sun in your mind's eye, a perfect sphere of glowing gas 109 times wider than Earth, burning with the light of 400 trillion watts, yet doing so with such steadiness that we can set our clocks by it. The Sun is always there, holding the planets in their orbits, bathing the solar system in light, protecting us from cosmic dangers we never even see. It's been doing this job for longer than Earth has existed, and it will continue long after humanity is gone, patient and eternal, the heart of our cosmic home. Let that constancy wash over you now, that sense of ancient, enduring stability. The solar cycle continues its rhythm, sunspots appearing and fading in their 11-year dance, solar flares occasionally erupting in beautiful arcs of plasma that loop hundreds of thousands of miles out into space before falling back to the surface. Even these seemingly violent events follow predictable patterns, occurring most frequently during solar maximum and becoming rare during solar minimum. The Sun's activity can be monitored and anticipated, making it one of the most studied and best understood stars in the entire galaxy. During the current solar cycle, Cycle 25, which began in December 2019, scientists predict that the maximum will occur sometime around 2025, bringing with it an increase in sunspots, solar flares, and auroral displays here on Earth. But even during maximum, the Sun remains remarkably stable by stellar standards. Some stars undergo violent outbursts that would sterilize any planets orbiting them, but our Sun is a relatively calm, middle-aged star that has found its comfortable rhythm. And so the Sun continues its ancient work, day after day, year after year, century after century, millennium after millennium, converting matter into energy, holding the solar system together, and providing the light and warmth that makes our planet bloom with life. It asks nothing in return for this service. It simply shines, as it has always shone, as it will continue to shine, a steady presence in an often unpredictable universe. Rest in that steadiness now. Let the image of that golden sphere fill your mind, and know that whatever changes tomorrow brings, the Sun will rise again, just as it has for 4.5 billion years. That is a kind of permanence we can truly rely on. Mercury, the swift and silent messenger. Let us drift now to the closest planet to our Sun, the small, swift world called Mercury. If you could stand on Mercury's surface, not that you'd want to, with temperatures that swing from scorching hot to bitterly cold, you would find yourself in one of the quietest places in the solar system. Mercury has virtually no atmosphere, just the thinnest possible whisper of an exosphere made up of atoms blasted from the surface by the solar wind and micrometeorite impacts. Sound cannot travel through this almost non-existent atmosphere, which means Mercury is a world of absolute silence. No wind whistles, no weather patterns rumble, no sounds disturb the ancient craters that cover its gray, moon-like surface. This silence has persisted for billions of years. Mercury formed 4.5 billion years ago from the same swirling disk of dust and gas that created all the planets, and it has remained essentially unchanged ever since. The craters you would see on Mercury today were blasted into its surface billions of years ago during a period called the Late Heavy Bombardment, when asteroids and comets rained down on all the inner planets. These craters have sat there undisturbed for countless ages, with no wind or water to erode them away, no geological activity to erase them. They are frozen in time, eternal monuments to the violent youth of our solar system. Mercury moves through space faster than any other planet, racing around the Sun at nearly 29 miles per second. That's over 100,000 miles per hour. It completes one full orbit in just 88 Earth days, which is why it was named after the swift-footed messenger god of Roman mythology. From Earth, we see Mercury darting back and forth across the sky, never straying far from the Sun, appearing alternately as a morning star before sunrise and an evening star after sunset. But despite its rapid orbit, Mercury has an extraordinarily slow rotation. The planet spins so leisurely that it takes 59 Earth days for Mercury to complete one full rotation on its axis. This creates one of the most unusual day-night cycles in the entire solar system. Because Mercury rotates 3 times for every 2 orbits it completes around the Sun, a ratio astronomers call a 3-to-2 spin-orbit resonance. The length of time from sunrise to sunrise on Mercury is actually 176 Earth days. That's longer than a Mercurian year, which remember is only 88 days long. So on Mercury, a single day lasts longer than 2 of its years. Imagine standing on Mercury's equator during this long, slow sunrise. The Sun would appear more than 3 times larger than it does from Earth, a massive golden disk dominating the sky. Because of Mercury's elliptical orbit and its unusual rotation, the Sun would do something truly strange. In some locations on Mercury, the Sun would rise partway, then reverse course and set again before rising once more and continuing its arc across the sky. At sunset, the process would repeat in reverse. The Sun would set, rise briefly, then set again for good. This cosmic dance happens because Mercury orbits the Sun at different speeds depending on where it is in its elliptical path, and at certain points, the orbital motion temporarily overtakes the rotational motion, making the Sun appear to backtrack in the sky. This long day means that any given spot on Mercury spends about 88 continuous Earth days in direct sunlight. During this time, temperatures at the surface can soar to 800 degrees Fahrenheit, hot enough to melt lead, tin, and zinc. But Mercury has virtually no atmosphere to trap this heat or distribute it around the planet. So when night finally arrives after those long, bright days, temperatures plummet rapidly. The night side of Mercury can drop to minus 290 degrees Fahrenheit, colder than anywhere on Earth's surface. And yet, there's something almost meditative about this extreme simplicity. Mercury doesn't have seasons. Its axis of rotation is tilted by less than 1 degree, essentially perfectly upright, so there's no variation throughout its year. There are no weather patterns to worry about, no storms brewing, no clouds gathering. There are no plate tectonics shifting the ground beneath your feet. Mercury is geologically dead, its interior having cooled and solidified long ago, with only a partially molten core remaining at its center. The planet has settled into a state of serene inactivity. Despite being so small, only about 1/3 the width of Earth, roughly the size of our Moon plus 40%, Mercury has a surprisingly strong magnetic field. It's only about 1% as strong as Earth's field, but its mere existence is remarkable for such a small planet. This magnetic field is generated by the partially liquid iron core at Mercury's center, which makes up an enormous proportion of the planet's mass. In fact, Mercury has the highest density of any planet in the solar system except for Earth, because this metallic core takes up about 85% of the planet's radius. If you could somehow crack Mercury open, you'd find that it's essentially a giant iron ball with only a thin shell of rocky crust on the outside. This large core may have formed because of a catastrophic collision early in Mercury's history. Scientists think that another planet-sized object struck Mercury with tremendous force, stripping away much of its original rocky mantle and leaving behind the metal-rich core. If this happened, it occurred so long ago, probably within the first few 100 million years of the solar system's formation, that Mercury has long since healed from the impact, its surface pounded smooth by billions of years of micrometeorite bombardment. Walking across Mercury's surface, again, in your imagination, you would find a landscape dominated by impact craters of every size. The largest is called the Caloris Basin, a massive impact scar 1,550 kilometers across, the result of an asteroid collision so powerful that it sent shockwaves through the entire planet. On the opposite side of Mercury from Caloris, the landscape is chaotic and jumbled. Scientists think this is where the seismic waves from the Caloris impact converged, disrupting the surface even halfway around the world. Between the craters, you'd find smooth plains of ancient lava flows, evidence that Mercury once had volcanic activity in its distant past. There are also strange features called scarps, long, winding cliffs that can be hundreds of kilometers long and up to a mile high. These formed as Mercury's interior cooled and contracted, causing the planet to shrink slightly and wrinkle its surface like the skin of a dried apple. These scarps are thought to have formed billions of years ago, and they have remained essentially unchanged ever since. At Mercury's poles, there are regions that never receive direct sunlight, deep craters where the sun never shines because of the planet's minimal axial tilt. Within these permanently shadowed craters, temperatures never rise above a couple hundred degrees below zero, and surprisingly, scientists have discovered deposits of water ice. Yes, ice exists on Mercury, the closest planet to the sun, hiding in these eternally dark refuges. The ice probably came from comets that impacted Mercury long ago, and it has persisted for millions or even billions of years, protected from the sun's fierce heat by the simple geometry of shadows. There's something profoundly peaceful about Mercury's simplicity. It doesn't try to be anything other than what it is, a small, dense, cratered world following its swift orbit with mathematical precision. 3 times it rotates for every 2 trips around the sun, over and over, a rhythm that has continued for billions of years and will continue for billions more. The craters sit in silence. The surface bakes during the long day and freezes during the long night, and Mercury asks nothing of us except perhaps our curiosity and our wonder. From Earth, we can occasionally watch Mercury transit across the face of the sun, a tiny black, taking several hours to crawl from one side of our star to the other. These transits happen only about 13 times per century, when Mercury's orbit carries it directly between Earth and the Sun. The next such transit won't occur until 2032, and watching one is a reminder of the clockwork precision with which the planets move through space. Only 2 spacecraft have ever visited Mercury, Mariner 10 in the 1970s and Messenger in the 2000s. Messenger orbited Mercury for 4 years, mapping its entire surface and measuring its magnetic field and composition before finally running out of fuel and crashing into the surface in 2015, adding one more crater to Mercury's already crater-saturated landscape. Currently, the Bepi-Colombo mission, a joint project between European and Japanese space agencies, is on its way to Mercury, using multiple gravity assists from Earth, Venus, and Mercury itself to slowly match orbits with the swift little world. It will arrive in 2025, ready to study Mercury in even greater detail than Messenger did. These missions have revealed Mercury to be more complex than its appearance suggests, a world of stark contrasts and subtle mysteries. But they have also confirmed its essential nature as a place of stillness and constancy, a planet that has found its equilibrium and maintains it with unwavering dedication. As you imagine Mercury now, see it as a small gray sphere racing through space in perfect silence, its cratered surface holding the memories of eons, its long days and nights following their inexorable rhythm. Let Mercury's simplicity remind you that sometimes the most peaceful state is simply to be, without change, without drama, constant and still, like a stone worn smooth by time. Venus, the cloud-wrapped evening star. Now let us journey to Venus, the second planet from the Sun and Earth's closest planetary neighbor. Of all the celestial objects in our night sky, only the moon shines more brightly than Venus. The ancient Romans named it for their goddess of love and beauty, and it's easy to see why. When Venus appears in the evening sky just after sunset, or in the morning sky just before dawn, it gleams with a brilliant, steady light that has captivated humanity for thousands of years. Poets have written odes to it, lovers have made wishes upon it, and astronomers have studied it with fascination for centuries. But Venus guards her secrets well. What makes Venus so bright is also what keeps her mysterious. A thick, unbroken layer of clouds that completely enshrouds the planet, reflecting 70% of the sunlight that falls upon it back into space. These aren't the fluffy white water vapor clouds we see on Earth. They're clouds made primarily of sulfuric acid droplets, floating in an atmosphere dominated by carbon dioxide. The cloud deck is so thick and so complete that until spacecraft began exploring Venus in the 1960s and 70s, nobody had ever seen the surface of Venus. To the naked eye, through a telescope, even through powerful instruments, Venus appears as a featureless, brilliant white disk. These clouds create one of the most Earth-like features on Venus, rain. But this is not refreshing water rain. On Venus, it rains sulfuric acid, though the raindrops never reach the surface. The atmosphere is so hot that the acid evaporates while still high in the atmosphere, creating a continuous cycle of precipitation that never quite completes. It's a ghost rain, falling eternally through the dense, hot air but never touching the ground. The atmosphere of Venus is extraordinarily massive, about 90 times denser than Earth's atmosphere at the surface. If you could stand on Venus, you would feel pressure equivalent to being 3,000 feet underwater in Earth's oceans. This immense atmosphere presses down with crushing force, but it also creates a strange kind of stability. The temperature and pressure on Venus's surface are remarkably constant, about 867 degrees Fahrenheit everywhere, all the time, day or night, equator or poles. The thick atmosphere distributes heat so efficiently that there are essentially no temperature variations across the entire planet. This extreme heat makes Venus the hottest planet in the solar system, even though Mercury is closer to the Sun. The carbon dioxide atmosphere traps heat in a runaway greenhouse effect, the most extreme example we know of in our solar system. Any heat that reaches the surface becomes trapped, unable to radiate back into space, building up to temperatures high enough to melt lead. And yet, there's something almost hypnotic about this absolute uniformity. Venus has no seasons, no weather fronts, no temperature variations. It's hot everywhere, always, with a consistency that would be terrifying if it weren't so strangely mesmerizing. Venus also rotates in a unique way. Unlike most planets, which spin in the same direction they orbit the Sun, Venus rotates backward, a phenomenon called retrograde rotation. If you could see the Sun through Venus's thick clouds, you would watch it rise in the west and set in the east. Scientists aren't entirely sure why Venus rotates backward, but one theory is that a massive collision early in Venus's history knocked the planet into this unusual spin. More remarkable still is how slowly Venus rotates. It takes 243 Earth days for Venus to complete one full rotation on its axis, which means a Venusian day is longer than a Venusian year. It takes Venus only 225 Earth days to orbit the Sun. Because of this and the retrograde rotation, a day on Venus, measured from sunrise to sunrise, lasts 116 3/4 Earth days. So if you were on Venus, you would experience fewer than 2 days in a Venusian year. But you would never actually see the sunrise anyway, because the clouds are so thick that only 10% of the sun's light reaches the surface, creating a perpetual dim twilight. The light levels on Venus's surface are similar to an overcast day on Earth. Bright enough to see clearly, but with no direct sunlight, no sharp shadows, no brilliant blue sky. Just an even, orangish glow filtered through hundreds of miles of sulfuric acid clouds. Above the surface, in the clouds themselves, something remarkable happens. The clouds of Venus race around the planet at tremendous speeds, completing one full circuit in just 4 days. These superrotating winds can reach speeds of over 300 miles per hour at the cloud tops, even though Venus itself is barely rotating at all. This superrotation is one of the great mysteries of planetary science. How can the atmosphere of a planet rotate 60 times faster than the planet itself? The wind at the surface is much calmer, only a few miles per hour, but because the atmosphere is so dense, even these gentle breezes can move small rocks and erode the landscape. The surface of Venus is a world of volcanic plains, with over 80% of the surface covered by ancient lava flows. There are volcanoes scattered across the landscape, some of them potentially still active, along with strange features called pancake domes, circular formations of hardened lava that are dozens of miles across and a mile or two high. Venus also has mountains, including Maxwell Montes, which rises 7 miles above the surrounding plains, higher than Mount Everest. There are vast highland regions, steep canyons, and impact craters, though far fewer craters than on Mercury or the Moon because Venus's thick atmosphere protects it from smaller impacts, and because volcanic activity may have resurfaced much of the planet relatively recently in geological terms, perhaps 500 million years ago. Despite its hellish surface conditions, there has been speculation about the possibility of life in Venus's upper atmosphere, where temperatures and pressures are much more moderate. At an altitude of about 30 to 40 miles above the surface, the atmospheric pressure is about the same as at sea level on Earth, and temperatures range from a comfortable 68 degrees to 149 degrees Fahrenheit. Some scientists have proposed that microscale microorganisms might be able to survive in this more temperate zone, floating in the sulfuric acid clouds. In 2020, scientists announced the potential detection of phosphine in Venus's atmosphere, a gas that on Earth is primarily produced by biological processes. This sparked tremendous excitement and debate, though subsequent analyses have questioned whether the signal was actually phosphine and, if it was, whether there might be non-biological explanations. The possibility of life on Venus remains speculative, but it reminds us that even in the most hostile environments, life might find a way to persist. Venus has been visited by more spacecraft than any other planet except Mars. The Soviet Union's Venera program sent a series of landers to Venus's surface, several of which successfully transmitted data for about an hour before being destroyed by the extreme heat and pressure. These missions sent back the only photographs we have ever taken from Venus's surface, orange-tinted images of a rocky desert stretching to a close horizon, under a thick, glowing sky. The landers showed temperatures so high that the electronics began to melt, pressure so intense that the spacecraft were slowly crushed. Yet in that brief window, they revealed a landscape both alien and oddly serene in its stillness. From orbit, radar mapping missions like NASA's Magellan spacecraft have revealed the detailed topography of Venus hidden beneath the clouds. These maps show a world of volcanic formations, tectonic features, and impact craters, all preserved in remarkable detail because there's no water erosion to wear them away. The surface of Venus is ancient yet young, resurfaced by volcanism but then frozen in time. As you imagine Venus now, picture it as a glowing orb wreathed in thick, sulfur-yellow clouds, spinning slowly backward in space, its surface hidden beneath an atmosphere so dense you could practically swim through it. The clouds race around the planet in their 4-day superrotation while the planet itself turns with painful slowness. Day and night are nearly indistinguishable on the surface, just different shades of dim, orange-tinted twilight lasting for months at a time. Venus reminds us that beauty can hide harshness, that bright things can conceal darkness, and that even in the most extreme conditions, there is a kind of terrible majesty. The planet maintains its thick blanket of clouds, its scorching surface, its backward rotation, all in perfect equilibrium. Venus is not trying to be like Earth, it is fully, completely itself, a world that followed its own evolutionary path to arrive at its current state. A cautionary tale perhaps, but also a fascinating example of how diverse the planets in our solar system can be. Let the image of Venus drift through your mind now. The brilliant evening star that has guided travelers and inspired poets, the cloud-wrapped world that keeps its secrets, the planet that once might have been more like Earth, with oceans and a habitable climate, before the greenhouse effect consumed it. Venus follows its orbit with the same mathematical precision as all the planets, appearing in our evening sky for months at a time as the evening star, then shifting to the morning sky as the morning star, marking time with a regularity that our ancestors used to track the seasons. It is constant in its extremes, predictable in its motions, and beautiful in its own fierce way, glowing like a diamond in the velvet darkness of space. Earth, our pale blue haven. And now we come home, to Earth, the third planet from the Sun, our home world, the only place in the entire universe where we know for certain that life exists. From space, Earth appears as a pale blue marble suspended in the black vastness, swirled with white clouds, touched with the browns and greens of land, ringed by the deep blue of ocean. The astronaut Carl Sagan once called it a pale blue, a mote of dust suspended in a sunbeam, and from great distances, that's exactly what Earth looks like, a single pixel of light carrying everything we've ever known. But up close, Earth is breathtaking in its complexity and beauty. 71% of the surface is covered by oceans, vast bodies of salt water that cradle life in incredible abundance and diversity. The oceans regulate our climate, driving weather patterns and distributing heat around the globe, creating the relatively mild conditions that allow liquid water to exist at the surface, a rare and precious state in the universe. Water can only exist as a liquid within a narrow temperature range, and Earth sits in what astronomers call the habitable zone or Goldilocks zone around the Sun. Not too hot, not too cold, but just right for liquid water to flow. This water, combined with an atmosphere rich in nitrogen and oxygen, creates conditions perfect for life as we know it. The atmosphere is thick enough to protect us from the harsh radiation of space and the sun, thin enough to allow sunlight through to warm the surface, and composed of gases that plants can use for photosynthesis and animals can breathe. It's a delicate balance, this atmosphere, maintained in part by the very life that depends upon it. Plants producing oxygen, oceans absorbing carbon dioxide, the whole system in a complex equilibrium. Earth spins on its axis once every 24 hours, creating the steady rhythm of day and night that governs so much of life's behavior. We wake with the sunrise, wind down with the sunset, our bodies tune to this ancient cycle. Earth is tilted on its axis by 23.5 degrees, and as we orbit the sun, this tilt causes the seasons. Summer when your hemisphere tilts toward the sun, winter when it tilts away, and the mild transitions of spring and autumn in between. This axial tilt creates the endless variety of climate zones across our planet. From the frozen poles to the tropical equator, each region with its own character, its own forms of life perfectly adapted to local conditions. But Earth doesn't travel through space alone. We have a companion, the Moon, Earth's only natural satellite. The Moon is unusually large for a moon relative to its planet. It's about 1/4 the diameter of Earth, which makes the Earth-Moon system almost a double planet in some ways. The Moon formed about 4.5 billion years ago, probably when a Mars-sized object crashed into the young Earth in a catastrophic impact that vaporized part of Earth's mantle and sent debris into orbit, where it gradually coalesced into the Moon. The Moon has been Earth's steady companion ever since, orbiting us once every 27.3 days. It's also gradually receding from Earth, moving about 1.5 inches farther away each year due to tidal interactions. But this happens so slowly that the change is imperceptible on human timescales. The Moon will remain our companion for billions of years to come. The Moon's gravitational influence on Earth creates the tides, the rhythmic rising and falling of ocean waters that has shaped coastlines and influenced life for all of Earth's history. Twice each day, most coastlines experience high tide and low tide as the Moon's gravity pulls on the oceans. This creates complex ecosystems in tidal zones, areas that are sometimes underwater and sometimes exposed to air. And many forms of life have evolved to take advantage of these predictable cycles. The Moon also stabilizes Earth's axial tilt. Without the Moon, Earth would wobble much more dramatically on its axis over thousands of years, leading to chaotic climate changes that might make the development of complex life much more difficult. The Moon serves as a kind of gyroscopic stabilizer, helping keep Earth's tilt relatively constant and therefore keeping our climate relatively stable on long timescales. It's one more way that conditions on Earth are just right for life to flourish. When we look at the Moon from Earth, we always see the same face. This is because the Moon is tidally locked to Earth, meaning it rotates once on its axis in exactly the same time it takes to orbit Earth once. This synchronous rotation means one hemisphere of the Moon always faces Earth and the other hemisphere always faces away. The far side of the Moon was a complete mystery until spacecraft orbited the Moon and photographed it. It looks similar to the near side but has far fewer of the dark planes called Maria, which on the near side form the features we imagine as the man in the Moon. The moon has no atmosphere, no weather, no water, no life. Its surface is covered with impact craters from billions of years of meteorite bombardment, along with the Maria, vast plains of ancient lava that erupted billions of years ago when the moon's interior was still hot and geologically active. Today the moon is geologically dead, a silent, airless world that reflects the sun's light to softly illuminate our nights. Looking at Earth from the moon, as the Apollo astronauts did, must have been one of the most moving experiences imaginable. There, rising above the moon's stark gray horizon, would be Earth, a swirled sphere of blue and white and brown, the only colorful thing in the entire scene, glowing against the black backdrop of space. Every human being who has ever lived, every story ever told, every achievement and struggle and moment of joy or sorrow, all contained on that one beautiful, fragile sphere. Earth's atmosphere creates beautiful phenomena visible from space. The delicate threads of hurricanes spinning over oceans, the vast swirls of jet streams in the upper atmosphere, the green and red auroras dancing near the poles when solar wind interacts with Earth's magnetic field. At night, the electric lights of cities create glowing webs across the continents, marking human civilization's footprint on the planet. From Earth, looking up at the sky, we see the same sky that our ancestors saw thousands of years ago. The stars will overhead in their nightly rotation, the constellations marking the seasons as Earth orbits the sun. The planets wander among the fixed stars. Mars with its orange glow, Jupiter bright and steady, Saturn dimmer but unmistakable to those who know where to look. And always there is the moon, waxing and waning through its phases, new moon to crescent to half to gibbous to full and back again, a 29.5-day cycle that has measured time for countless generations. Earth maintains a magnetic field generated by the churning of molten iron in its outer core. This magnetic field extends thousands of miles into space, creating the magnetosphere that deflects most of the solar wind and cosmic rays that would otherwise bombard the surface. The magnetic field is what makes compasses work, always pointing toward magnetic north. And it's what creates the auroras when charged particles spiral down the magnetic field lines and collide with atmospheric gases near the poles. The surface of Earth is constantly changing, shaped by the forces of plate tectonics. The crust is broken into several large plates that slowly drift across the surface, driven by heat from the interior. Where plates collide, mountain ranges rise. Where they pull apart, new ocean floor forms. Where one plate slides beneath another, volcanic chains erupt. This geological activity recycles Earth's crust, ensuring that over millions of years, old crust is destroyed and new crust created, keeping the planet geologically young despite its 4.5 billion year age. Life on Earth has shaped the planet just as surely as geological forces have. Plants turn the atmosphere from one dominated by carbon dioxide to one rich in oxygen, enabling the evolution of complex animal life. Coral reefs build massive structures from calcium carbonate. Forests influence weather patterns and water cycles. Life and Earth have co-evolved over billions of years, each shaping the other in an intricate dance of cause and effect. And here we are, conscious beings able to contemplate our own existence, to look up at the stars and wonder about our place in the cosmos. Earth is our home, the cradle of humanity, and perhaps one day we will venture out to other worlds. But we will always carry Earth with us, in our bodies adapted to its gravity, in our need for its air and water, in our psychological attachment to the landscapes and seascapes that shaped our evolution. As you rest now, imagine Earth as the astronauts see it from space. Whole and complete, the clouds drifting slowly across the blue oceans, the continents visible through gaps in the white, the thin blue line of atmosphere clinging to the surface like a delicate membrane. Imagine the billions of living things going about their lives, the tides rising and falling, the seasons turning, the water cycling from ocean to clouds to rain to rivers and back to ocean again. Earth is a living system, dynamic and complex, yet stable enough that conditions have remained favorable for life for billions of years. Let the knowledge of Earth's perfect position, its protective atmosphere, its life-giving water, its stabilizing moon, all wash over you now. You are home, on a planet that has everything you need, spinning through space at a comfortable distance from the sun, wrapped in a blanket of air, blessed with water and life. Earth continues its journey, orbiting the sun once every 365.25 days, rotating once every 24 hours, maintaining its tilt, hosting its moon, all in the most elegant, automatic way imaginable. Rest here on this pale blue dot and know that you are exactly where you belong. Mars, the rusty red world of quiet deserts. Let us journey now to the fourth planet from the Sun, Mars, the rusty red world that has captivated human imagination for centuries. Mars appears in our night sky as a distinctly orange-red star, and this color gave it its name. The Romans called it Mars after their god of war because the red color reminded them of blood. But up close, Mars is less a world of violence and more a world of quiet desolation. A frozen desert where dust devils dance across ancient plains and the wind whispers through vast canyons. Mars is about half the diameter of Earth and has only about 1/10 of Earth's mass, making it a significantly smaller world. But it's large enough to have maintained some geological activity through much of its history, and the evidence of that activity is written across the Martian landscape in spectacular fashion. Mars has the largest volcano in the entire solar system, Olympus Mons, a shield volcano that rises 16 miles above the surrounding plains, nearly 3 times the height of Mount Everest. The base of Olympus Mons spans roughly the same area as the state of Arizona, making it not just tall but immense in every dimension. The existence of such a massive volcano tells us that Mars once had significant geological activity. Olympus Mons and the other large volcanoes in the Tharsis region formed over millions or billions of years as magma from the interior pushed its way to the surface. Unlike Earth, where plate tectonics would eventually move a volcano away from its magma source, Mars has no plate tectonics, so volcanic hotspots remain stationary, allowing volcanoes to grow to enormous sizes as they erupted repeatedly in the same location. Mars also hosts the longest and deepest canyon system in the solar system, Valles Marineris, a vast scar that stretches nearly 2,500 miles along the Martian equator, up to 4 miles deep and 400 miles wide in places. This canyon system formed not through water erosion like the Grand Canyon on Earth, but through tectonic activity as the Tharsis region bulged upward billions of years ago, cracking and stretching the crust. Some sections of Valles Marineris may have been subsequently modified by water erosion when Mars had a thicker atmosphere and liquid water on its surface, but the primary structure is tectonic. Evidence of ancient water is everywhere on Mars. Orbital spacecraft have photographed ancient river valleys, lake beds, and what appear to be ocean shorelines. The northern third of Mars is significantly lower in elevation than the southern highlands, and some scientists think this vast northern depression may have once held an ocean covering nearly a third of the planet's surface. If this ocean existed, it would have been billions of years ago, when Mars was warmer and wetter with a much thicker atmosphere. Today, Mars is cold and dry. The average surface temperature is about -80 degrees Fahrenheit, though it can warm up to a relatively comfortable 50 to 70 degrees at the equator during summer afternoons. But nights are bitterly cold, and the atmosphere is thin, less than 1% of Earth's atmospheric pressure at the surface. This thin atmosphere is composed primarily of carbon dioxide, with trace amounts of nitrogen and argon. The thin atmosphere means that Mars has very little greenhouse warming, and heat escapes rapidly into space once the sun sets. It also means that Mars has very little protection from ultraviolet radiation and cosmic rays, making the surface hostile to life as we know it. But the atmosphere is thick enough to support weather, including clouds, frost, and even snow in some regions. Mars experiences dust storms, some of which can grow to encompass the entire planet. These global dust storms happen unpredictably, roughly once every 3 to 5 Martian years, and when they occur, they can last for months, coating the entire planet in a haze of fine dust that obscures the surface from view. The storms typically begin during Martian spring and summer in the southern hemisphere, when Mars is closest to the Sun in its elliptical orbit. The extra heating creates strong temperature gradients that drive powerful winds, lifting dust into the atmosphere. But even these planet-wide dust storms, while dramatic from a meteorological perspective, are gentle by Earth standards. The atmospheric pressure on Mars is so low that even high-speed winds carry very little force. A 100-mile-per-hour wind on Mars would feel more like a gentle breeze on Earth, though it would still be powerful enough to lift fine dust particles and transport them across vast distances. Between the major storms, Mars experiences more typical weather. Smaller dust devils that spiral across the plains, seasonal patterns of frost forming and sublimating, and the slow drift of water ice clouds through the thin atmosphere. At the poles, carbon dioxide freezes out of the atmosphere during winter, forming seasonal ice caps that can extend down to mid-latitudes before sublimating back into gas during spring and summer. Beneath these seasonal caps are permanent ice caps made of water ice, especially prominent at the North Pole, where a cap of water ice nearly 2 miles thick sits year-round. Mars has 2 small moons, Phobos and Deimos, both probably captured asteroids rather than moons that formed alongside Mars. Phobos is the larger of the two, about 14 miles across at its widest, and it orbits so close to Mars, only about 3,700 miles above the surface, that it actually orbits Mars faster than Mars rotates. This means that from the Martian surface, Phobos would appear to rise in the west and set in the east, crossing the sky in just a few hours. Phobos is also gradually spiraling inward toward Mars, and in about 50 million years, it will either crash into the planet or break apart due to tidal forces, forming a ring around Mars. Deimos is smaller, only about 8 miles across, and orbits much farther out, taking about 30 hours to orbit Mars. From the Martian surface, Deimos would appear as a bright star slowly moving across the sky over the course of more than 2 days from moonrise to moonset. Both moons are heavily cratered and irregularly shaped, looking more like potatoes than spheres. They're among the darkest objects in the solar system, reflecting only a small percentage of the sunlight that falls on them. Their surfaces are covered in a layer of fine dust, kicked up by countless micrometeorite impacts over billions of years. Mars rotates once on its axis in about 24.5 hours, remarkably close to Earth's 24-hour day. This makes a Martian day called a sol very similar in length to an Earth day. Mars is also tilted on its axis by about 25 degrees, close to Earth's 23.5-degree tilt, which means Mars experiences seasons much like Earth does. However, because Mars takes about 687 Earth days to orbit the Sun, Martian seasons are nearly twice as long as Earth seasons. The combination of familiar day length and seasonal cycles makes Mars feel, in some ways, like a home away from home, at least compared to other planets. If you could stand on Mars's surface in a proper spacesuit, you would see a butterscotch sky during the day. Tan or butterscotch-colored because of the fine dust perpetually suspended in the thin atmosphere. The Sun would appear about 2/3 the size it appears from Earth, a smaller but still bright disk hanging in that alien sky. At sunset on Mars, something magical happens. As the Sun dips toward the horizon, the sky near the Sun turns blue. This is the opposite of Earth, where sunsets paint the sky red and orange. On Mars, the dust in the atmosphere scatters red light, making most of the sky appear reddish. But near the Sun at sunset, blue light is forward scattered, creating a blue glow around the setting Sun. It's a hauntingly beautiful effect, captured by the various rovers that have explored Mars's surface. Speaking of which, Mars has been visited by more spacecraft than any other planet except Earth. Dozens of missions have been sent to Mars with varying degrees of success, and currently, several spacecraft orbit Mars while multiple rovers explore its surface. These missions have revealed Mars to be a world far more complex and interesting than the simple red dot visible from Earth. The rovers have found evidence that ancient Mars was once warmer and wetter, with liquid water flowing on the surface, forming rivers, lakes, and possibly oceans. They found minerals that only form in the presence of liquid water and discovered ancient lake bed sediments laid down layer by layer over millions of years. Some locations appear to have been habitable environments in the past, with the right conditions for microbial life as we know it, liquid water, energy sources, and organic molecules. Whether life actually arose on ancient Mars remains unknown. No definitive evidence of past or present life has been found, but the search continues. Future missions, including sample return missions currently in development, may finally answer this ancient question. If life ever existed on Mars, even as simple microbes, it would be one of the most profound discoveries in human history, telling us that life is not unique to Earth. In the meantime, Mars continues its patient orbit, a cold, dusty world that nevertheless stirs human dreams of exploration and eventual settlement. The planet rotates, the seasons turn, dust storms rise and fall, frost forms and sublimates, and the two tiny moons race across the sky. Mars is a world of deep time and quiet grandeur, where ancient volcanoes stand silent and vast canyons stretch empty toward the horizon. As you imagine Mars now, picture it as that rusty red sphere hanging in space, its polar ice caps gleaming white at the top and bottom, dark features visible through the butterscotch haze. The massive volcanoes rise in frozen majesty, the canyons cut deep and shadowed, and across the plains, the wind slowly, patiently reshapes the dust into dunes and ripples that will persist for years or centuries before changing again. Mars is a world of stillness and subtle motion, harsh yet beautiful, alien yet somehow familiar. A reminder that worlds can be quiet and cold and still possess a stark, undeniable splendor. Jupiter, the protective giant. Now we venture to the outer solar system, crossing the asteroid belt to reach Jupiter, the largest planet in our solar system and the first of the gas giants. Jupiter is enormous beyond easy comprehension. More than 11 times wider than Earth, with a mass greater than all the other planets combined. You could fit 1,321 Earths inside Jupiter's volume, and yet Jupiter spins faster than any other planet, completing one full rotation in less than 10 hours. This rapid rotation creates fierce winds and dramatic weather patterns, giving Jupiter its characteristic banded appearance. From a distance, Jupiter appears as a beautiful, complex sphere striped with alternating light and dark bands parallel to its equator. These bands are actually massive atmospheric currents. The light zones are regions of upwelling gases and high-altitude clouds, while the darker belts are regions where gases are descending. The boundaries between zones and belts spawn enormous storms, swirling vortices that can persist for centuries. The most famous of these is the Great Red Spot, a storm larger than Earth that has been raging for at least 350 years, possibly much longer. When astronomers first began observing Jupiter through telescopes in the 17th century, they noted a large spot on the planet, and it has been continuously observed since the mid-19th century. The Great Red Spot is actually shrinking slowly. It's now only about twice Earth's diameter, down from perhaps 4 times Earth's diameter a century ago, but it shows no signs of disappearing entirely anytime soon. The Great Red Spot rotates counterclockwise, taking about 6 days to complete one rotation. Its distinctive red color probably comes from complex organic compounds formed when sunlight breaks apart simple molecules in Jupiter's upper atmosphere. Wind speeds at the edge of the storm can reach up to 400 miles per hour, yet this massive storm has maintained its basic structure for centuries, a testament to the stability of Jupiter's atmospheric dynamics despite the planet's seemingly chaotic appearance. Jupiter's atmosphere is composed primarily of hydrogen and helium, the same materials that make up the Sun, though in different proportions. As you descend into Jupiter's atmosphere, the pressure and temperature increase rapidly. There's no solid surface. Instead, the gaseous atmosphere gradually transitions to a liquid state as the pressure builds. Deep in Jupiter's interior, the pressure becomes so intense that hydrogen is compressed into a state called metallic hydrogen, where it behaves like a liquid metal. This metallic hydrogen generates Jupiter's powerful magnetic field, the strongest of any planet in the solar system, about 20,000 times stronger than Earth's field. The magnetic field extends millions of miles into space, creating a magnetosphere so vast that it would appear several times larger than the full moon in our sky if we could see it with our naked eyes. This magnetosphere traps charged particles from the solar wind, creating intense radiation belts around Jupiter that pose challenges for spacecraft visiting the system. The magnetosphere also interacts with some of Jupiter's moons, particularly Io, stripping away material and creating electrical currents that flow between Jupiter and the Moon. Jupiter acts as a kind of cosmic protector for the inner solar system. Its enormous gravity influences the trajectories of comets and asteroids, and it has probably deflected or captured many objects that might otherwise have crashed into the inner planets. Some scientists think that without Jupiter's protective influence, Earth might have suffered far more impacts from comets and asteroids, potentially making it harder for complex life to evolve. In this way, Jupiter serves as a guardian, its gravity creating a safer inner solar system. Jupiter has at least 95 known moons, though that number keeps increasing as astronomers discover smaller and smaller satellites. 4 of these moons are particularly special. The Galilean moons, so named because Galileo Galilei discovered them in 1610 using one of the first telescopes ever pointed at the night sky. These 4 moons, Io, Europa, Ganymede, and Callisto, are worlds unto themselves, each with unique characteristics. Io is the innermost Galilean moon and the most volcanically active body in the entire solar system. Tidal forces from Jupiter, amplified by orbital resonances with Europa and Ganymede, squeeze and flex Io's interior, generating tremendous heat. This heat drives constant volcanic eruptions, with hundreds of active volcanoes covering the surface. Some of these eruptions are so powerful that they blast material more than 250 miles above the surface. The constant volcanic activity means that Io is constantly resurfacing itself, burying impact craters as fast as they form and making it one of the youngest surfaces in the solar system. Europa, the second Galilean moon, may be one of the most promising places to search for life beyond Earth. Its surface is covered by a shell of water ice crisscrossed with dark lines and ridges, giving it a cracked, fragmented appearance. But beneath this icy shell lies an ocean of liquid water, perhaps 60 miles deep, more water than all of Earth's oceans combined. Tidal heating from Jupiter keeps this ocean liquid despite Europa being so far from the Sun. The ocean is in contact with a rocky seafloor, which could provide minerals and chemical energy, and hydrothermal vents like those on Earth's ocean floor might exist, providing habitats for potential life. Ganymede is the largest moon in the solar system, even bigger than the planet Mercury. It's the only moon known to have its own magnetic field, probably generated by a liquid iron core deep in its interior. Like Europa, Ganymede also appears to have a subsurface ocean, though buried beneath a thicker ice shell. Its surface is a mix of heavily cratered dark regions and lighter grooved terrain, suggesting a complex geological history. Callisto is the outermost Galilean moon, and it has the most heavily cratered surface of any object in the solar system, indicating that its surface is extremely ancient, perhaps billions of years old, with little geological activity to erase the craters. Yet even Callisto may have a subsurface ocean, though its exact nature remains uncertain. These 4 moons orbit Jupiter in a beautiful dance governed by orbital resonances. For every 1 orbit Ganymede makes, Europa makes exactly 2 orbits, and Io makes exactly 4 orbits. This 3:1:2 resonance is not a coincidence but a stable gravitational configuration that the moons settled into long ago. As they orbit, they line up in specific patterns that repeat with clockwork precision, another example of the orderly mathematics underlying the apparent chaos of the cosmos. From Jupiter's cloud tops, the moons would be spectacular sights. Io would appear about 2/3 the size of our moon as seen from Earth, but would be noticeably orange and yellow. Europa would gleam brilliantly white, reflecting sunlight from its icy surface. Ganymede would appear even larger, and Callisto would be visible as a dimmer but still prominent disk. All 4 would be easily visible to the naked eye, wheeling around Jupiter in their elegant orbital dance, a miniature solar system within the solar system. Jupiter's atmosphere is never still. The zones and belts shift slowly over time, The great red spot drifts and changes size, smaller storms form and dissipate, and lightning bolts crackle through the clouds. Though Jupiter's lightning appears to be concentrated at the cloud tops rather than extending down to lower altitudes as on Earth. Despite this activity, there's something almost hypnotic about Jupiter's appearance. The bands flowing in alternating directions, the storms swirling in their vast gyres, all of it following the inexorable laws of fluid dynamics and thermodynamics. The Juno spacecraft, currently orbiting Jupiter, has revealed the planet's poles to be far more chaotic than the equatorial regions, with massive cyclones arranged in geometric patterns. At Jupiter's north pole, 8 cyclones surround a central cyclone, while at the south pole, 5 cyclones surround a central one. These polar storms are each several thousand miles across and have been stable in this configuration for years, spinning in their careful arrangement like gears in a cosmic machine. Jupiter also has a faint ring system discovered by the Voyager 1 spacecraft in 1979. These rings are much less prominent than Saturn's and are composed primarily of dust kicked up from Jupiter's small inner moons by micrometeorite impacts. The rings are so faint that they were completely unknown until spacecraft flew past Jupiter and photographed them in just the right lighting conditions. As you imagine Jupiter now, see it as that massive, swirling sphere 11 times wider than Earth, striped with bands of color, the great red spot like a bloodshot eye staring out into space. See the 4 bright Galilean moons arrayed around it like pearls on a string, each a world with its own story, its own possibilities. Feel Jupiter's gravitational presence, so strong that it shapes the orbits of countless objects throughout the outer solar system, so powerful that it helps protect the inner planets from cosmic impacts. Jupiter is stability through size, a massive anchor in the solar system that follows its 12-year orbit with unwavering precision. The king of planets, ancient peoples called it, and the name fits, massive, powerful, commanding, yet maintaining order through its very presence. Let Jupiter's grandeur fill your mind, that sense of vast scale, of ancient storms that rage for centuries, of hidden oceans beneath icy moons, of a miniature planetary system dancing in orbital resonance. Jupiter is constancy writ large, the proof that even the largest and most complex systems can maintain order and pattern across billions of years. Saturn, the ring jewel. Beyond Jupiter lies Saturn, perhaps the most visually stunning planet in the entire solar system. Even through a small telescope, Saturn takes your breath away. A golden sphere surrounded by magnificent rings that make it instantly recognizable. Saturn is the second largest planet, about 9 times wider than Earth, and like Jupiter, it's a gas giant composed primarily of hydrogen and helium. But while Jupiter appears chaotic and turbulent, Saturn has a more serene quality, its atmosphere marked by subtler bands and gentler features. Saturn's most remarkable feature is, of course, its rings. Vast, flat disks of countless particles orbiting the planet in a thin plane aligned with Saturn's equator. These rings extend hundreds of thousands of miles from Saturn but are remarkably thin, in some places only about 30 feet thick. If you could shrink Saturn and its rings down proportionally, the rings would be thinner than a sheet of paper compared to the planet. The rings are composed primarily of water ice particles ranging in size from tiny grains like fine sand to chunks as large as houses or even mountains. Each individual particle follows its own orbit around Saturn, held in place by the planet's gravity. The rings are divided into several main sections labeled with letters in the order they were discovered. The most prominent are the A ring, the B ring, and the C ring, with several fainter rings and gaps between and beyond the main rings. The gaps in the rings are caused by gravitational interactions with Saturn's moons. For example, the Cassini division, the largest gap in the rings, is cleared by the moon Mimas. Particles in this region orbit Saturn twice for every one orbit Mimas makes, and this 2-to-1 resonance causes those particles to be pushed out of that region over time. Other gaps are maintained by small moons called shepherd moons that orbit within or near the rings, their gravity hurting the ring particles and creating sharp edges. The origin of Saturn's rings remains somewhat mysterious. They could be the remains of a moon that was destroyed by a collision or torn apart by tidal forces when it strayed too close to Saturn. Alternatively, they might be primordial material left over from Saturn's formation that never coalesced into a moon. Recent observations suggest the rings might be relatively young by cosmic standards, perhaps only a few 100 million years old rather than as ancient as Saturn itself. This would mean the magnificent ring system we see today is temporary on cosmic timescales, which makes us fortunate to live in an era when Saturn's rings are so prominent. Saturn's atmosphere, while less dramatically banded than Jupiter's, still shows distinct zones and belts along with occasional massive storms. Every roughly 30 Earth years, one Saturnian year, a colossal storm erupts in Saturn's northern hemisphere, called the Great White Spot. These storms grow to encircle the entire planet, lasting for months before fading away. The most recent Great White Spot appeared in 2010 and 2011, and astronomers were able to study it in unprecedented detail using the Cassini spacecraft that was orbiting Saturn at the time. Saturn also hosts one of the strangest atmospheric features in the solar system, a hexagonal jet stream that encircles the North Pole. This hexagon is about 20,000 miles across, each side longer than Earth's diameter, and it has persisted for decades. The hexagonal shape is thought to arise from the interaction of winds moving at different speeds, but the exact mechanisms that create and maintain such a geometrically precise pattern remain the subject of ongoing research. Inside the hexagon is a massive hurricane-like storm, swirling at the exact pole, its eye about the size of Earth. Saturn rotates quickly despite its size, completing one rotation in about 10.5 hours. This rapid spin causes the planet to bulge noticeably at the equator, giving Saturn the most oblate shape of any planet. It's visibly flattened, about 10% wider at the equator than from pole to pole. This also creates strong winds in Saturn's atmosphere, with jet streams reaching speeds of over 1,000 miles per hour near the equator. Saturn's density is remarkably low. In fact, it's the only planet in the solar system less dense than water. If you could find an ocean large enough, Saturn would float. This low density comes from its composition of lightweight hydrogen and helium, along with its distance from the Sun, which allowed it to retain these light gases during its formation. Saturn has at least 146 known moons, more than any other planet, ranging from tiny moonlets embedded in the rings to massive Titan, the second largest moon in the solar system. Titan is extraordinary. It's the only moon with a substantial atmosphere, thicker than Earth's atmosphere, composed mostly of nitrogen with a small amount of methane. This atmosphere is so thick and hazy that the surface of Titan was completely hidden from view until the Cassini-Huygens mission sent a probe through the atmosphere to land on the surface in 2005. Titan's atmosphere creates weather, clouds form, and methane rain falls from the sky. But Titan is so cold, with surface temperatures around -290 degrees Fahrenheit, that methane and ethane are liquid, filling the role that water plays on Earth. Titan has lakes and seas of liquid methane and ethane near its poles, along with rivers and coastlines. It's the only place in the solar system besides Earth where stable bodies of liquid exist on the surface. The Huygens probe, which landed on Titan, sent back images of a landscape eerily similar to Earth in some ways. Rounded rocks or ice boulders sitting on a dark plain, with what appeared to be drainage channels carved into highlands in the distance. But the rocks were made of water ice as hard as stone in Titan's frigid temperatures, and the liquid that carved those channels was liquid methane, not water. Titan also has a subsurface ocean of liquid water, detected through careful measurements of the Moon's gravity field and how it responds to Saturn's tides. This ocean lies beneath an icy shell perhaps 50 miles thick. So Titan has two completely different liquid environments: a surface dominated by liquid methane and ethane, and a deep subsurface ocean of water. Both are potential habitats for life, though any life on Titan would be radically different from life on Earth. Another fascinating moon of Saturn is Enceladus, a small, icy world that's incredibly geologically active despite its small size. Enceladus shoots enormous geysers of water vapor and ice particles from cracks near its south pole, creating a plume that extends hundreds of miles into space. These geysers indicate that Enceladus has a subsurface ocean of liquid water, kept warm by tidal heating from Saturn. The plumes contain not just water but organic molecules and other compounds, suggesting that Enceladus's ocean might be habitable. The ice particles from Enceladus's geysers actually supply material to one of Saturn's rings. The faint E-ring is created by ice from Enceladus, making it a constant stream of new material. In a sense, Enceladus is constantly creating its own ring around Saturn. Saturn's magnetosphere is much weaker than Jupiter's but still substantial, extending far enough to encompass many of Saturn's inner moons. The interaction between the magnetosphere and particles from Enceladus's geysers creates beautiful auroras at Saturn's poles, glowing curtains of light similar to Earth's northern and southern lights but powered by a different mechanism. From Saturn's cloud tops, the view would be stunning beyond words. The rings would arch overhead, forming a magnificent bridge across the sky that would appear brighter than the full moon on Earth. Depending on your latitude, the rings might fill the sky from horizon to horizon or appear as a bright line cutting through the heavens. During Saturn's lengthy seasons, each lasting about 7.5 Earth years, the rings would cast vast shadows on the planet's clouds, creating dramatic patterns of light and dark. The moons would be visible against the black of space, Titan shining steadily with its thick, hazy atmosphere, Enceladus a distant point of light with its geysers creating a faint halo. Smaller moons would move across the sky, occasionally passing in front of the sun to create miniature solar eclipses. The sun itself would appear only about 1/100th as bright from Saturn as it does from Earth, but still bright enough to light the scene clearly. It would look similar to twilight on Earth, a permanent state of gentle daylight. Saturn orbits the Sun once every 29.5 Earth years, maintaining its graceful distance of about 900 million miles. Its axial tilt of about 27 degrees gives it seasons similar to Earth's, though each season lasts more than 7 years. As Saturn orbits, the angle from which we view its rings from Earth changes, creating a cycle where sometimes we see the rings wide open, showing their full glory, and other times we see them edge on, when they almost disappear from view because they're so thin. The next time Saturn's rings appear edge-on from Earth will be in 2025, a rare opportunity to study the ring's thickness and potentially spot small moons that normally get lost in the glare of the rings. Then, over the following years, the rings will slowly open up again, becoming fully visible by the early 2030s. As you imagine Saturn now, see it as that serene golden sphere adorned with rings like jewelry, a cosmic masterpiece of orbital dynamics and ice. See the rings extending outward, made of countless particles, each following its own precise path. The whole structure maintained by the subtle pushes and pulls of gravity from Saturn and its many moons. Picture the hexagonal storm at the North Pole, the lazy drift of clouds in the atmosphere, and the patient orbiting of Titan with its thick atmosphere and methane lakes. Saturn represents order arising from chaos, beauty emerging from physics, complexity from simple rules. The rings are not solid, but they appear solid, a billion separate particles moving in such perfect harmony that they create the illusion of a continuous structure. Saturn teaches us that elegance and spectacle can coexist with mathematical precision, that the most beautiful things in the universe often arise from the simplest physical principles: gravity, orbital motion, and time. Let Saturn's serene beauty fill your thoughts now, that sense of vast scales and delicate balances, of ancient patterns maintained across billions of years. Uranus and Neptune, the ice giant twins. Now we venture to the outermost reaches of the major planets, to Uranus and Neptune, the ice giants. These two worlds are fundamentally different from Jupiter and Saturn, smaller, denser, with less hydrogen and helium and more water, methane, and ammonia in their compositions. They represent the transition between the gas giants of the middle solar system and the small, icy worlds of the outer solar system. Uranus is the seventh planet from the Sun, orbiting at a distance of about 1.8 billion miles, so far away that it takes 84 Earth years to complete one orbit. Uranus is unique in the solar system because it rotates on its side. Its axis of rotation is tilted about 98 degrees, meaning the planet essentially rolls around the Sun like a ball rather than spinning like a top. This extreme tilt probably resulted from a massive collision with an Earth-sized object early in the solar system's history, an impact so violent that it knocked Uranus onto its side. This sideways rotation creates the strangest seasons in the solar system. For about 42 years, one pole of Uranus points generally toward the Sun while the other pole points away into darkness. Then, as Uranus continues its orbit, both poles experience a brief spring and autumn when they're edge-on to the Sun. Then the situation reverses, and the pole that was in perpetual daylight plunges into 42 years of darkness while the opposite pole emerges into sunlight. Imagine living through a day that lasts 42 years, followed by a night equally long. Despite this extreme axial tilt, Uranus appears remarkably featureless to our eyes. The planet is a pale blue-green color, the result of methane in its upper atmosphere absorbing red light and reflecting blue and green light back into space. Through most telescopes, Uranus appears as a nearly uniform disk with little visible structure. This bland appearance is quite different from the dramatic bands and storms we see on Jupiter and Saturn. However, high-resolution images from the Voyager 2 spacecraft and later observations from the Hubble Space Telescope and ground-based telescopes have revealed that Uranus does have atmospheric structure, faint bands, occasional bright clouds, and even some storms. The weather on Uranus just seems much more subdued than on the larger gas giants, perhaps because Uranus receives so little energy from the Sun at its great distance. Interestingly, Uranus emits very little heat from its interior, unlike the other gas and ice giants. Jupiter, Saturn, and Neptune all radiate more energy than they receive from the Sun, releasing heat left over from their formation or generated by gravitational contraction. But Uranus radiates barely any excess heat, possibly because the collision that tipped it over also disrupted its interior structure in some way that allowed much of its primordial heat to escape long ago. Uranus has a system of faint rings, discovered in 1977 when astronomers noticed that a star being occulted by Uranus blinked several times before and after the planet itself passed in front of it. The rings of Uranus are dark and narrow, composed of dust and small rocky particles rather than the ice particles that make up Saturn's rings. There are 13 known rings, labeled with numbers and Greek letters, all confined to a region relatively close to the planet. The planet also has 27 known moons, most of them named after characters from the plays of William Shakespeare and the poems of Alexander Pope, making Uranus unique among the planets for drawing its moon names from literature rather than mythology. The 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are substantial worlds in their own right, ranging from about 300 to 1,000 miles across. Miranda is particularly fascinating despite its small size. Its surface is a bizarre patchwork of different terrains, heavily cratered regions, grooved regions, and strange angular features that look completely unlike anything else in the solar system. The most dramatic feature is Verona Rupes, a cliff that plunges about 12 miles from top to bottom, making it the tallest known cliff in the solar system. If you jumped off Verona Rupes, you would fall for about 12 minutes before hitting the bottom, thanks to Miranda's low gravity. Neptune's deep blue tranquility. As you settle into stillness, let your thoughts drift far from Earth, outward through the solar system, toward a distant world wrapped in deep blue calm. Neptune is the most distant of the major planets, orbiting the Sun at an average distance of about 4.5 billion kilometers. From this far away, sunlight is faint and gentle, more like a distant glow than a source of warmth. Days and nights blur into a long, quiet twilight. Neptune's rich blue color comes from methane in its atmosphere. Methane absorbs red wavelengths of light, leaving behind shades of blue that feel cold, steady, and unchanging. There are no solid surfaces to stand on here. Instead, layers of gas slowly give way to denser regions under immense pressure. Despite its peaceful appearance, Neptune hosts the fastest winds ever measured in the solar system, reaching speeds of more than 2,000 kilometers per hour. These winds move through a vast atmosphere where storms can last for years. Yet from a distance, everything appears smooth and calm, like motion hidden beneath still water. Orbiting Neptune is Triton, its largest moon. Triton moves in the opposite direction of Neptune's rotation, a rare and unusual trait. Scientists strongly believe Triton was once a free object in the outer solar system before being captured by Neptune's gravity. Its surface is covered in frozen nitrogen, and spacecraft observations have revealed gentle nitrogen geysers rising slowly into the thin atmosphere. Neptune also has faint rings, far darker and thinner than those of Saturn. They are incomplete and uneven, made of ice and dust, quietly circling a planet that rarely draws attention to itself. Everything here feels distant, cold, and profoundly peaceful. The outer reaches, dwarf planets, and the Kuiper Belt. Beyond Neptune lies a vast region where the solar system fades into quiet obscurity. This is the realm of dwarf planets and the Kuiper Belt. The Kuiper Belt is a wide disk of icy objects extending far beyond Neptune's orbit. It contains remnants from the early solar system, preserved by distance and cold. These objects have remained largely undisturbed for billions of years. Pluto is the most familiar of the dwarf planets. Though no longer classified as a major planet, it remains one of the most scientifically important bodies in the outer solar system. Pluto's surface is a frozen landscape of nitrogen, methane, and carbon monoxide ice. Vast plains of frozen nitrogen stretch across its surface, alongside mountains made of water ice as hard as rock at such low temperatures. Pluto follows an elongated, tilted orbit, sometimes coming closer to the Sun than Neptune before drifting far back into the darkness. It has a thin atmosphere that appears when Pluto is closer to the Sun and freezes solid again as it moves away. Other dwarf planets share this quiet region. Eris, Makemake, and Haumea all move through peaceful, stable orbits, each with unique characteristics. Haumea spins so rapidly that it has an elongated shape, while Eris is slightly more massive than Pluto and resides even farther from the Sun. Surrounding all of this is the heliosphere's outer boundary. The heliosphere is a vast bubble formed by the solar wind, extending far beyond the planets. At its edge, the influence of the Sun gently fades, giving way to interstellar space. Spacecraft such as Voyager have crossed this boundary, confirming where the Sun's influence finally softens into the wider galaxy. Here, motion is slow. Change takes place over immense spans of time. Cosmic rhythms and celestial mechanics. As the solar system stretches outward, its movements follow rhythms that are steady and predictable. Planets and smaller bodies move in orbital resonances, where their gravitational interactions create long-lasting stability. Some objects complete 2 orbits in the same time another completes 3, forming patterns that can persist for millions or even billions of years. Gravity is the quiet architect of these motions. It balances speed and distance, ensuring that planets neither drift away nor fall inward. This balance creates an orderly system where motion feels calm, almost inevitable. Time in the solar system operates on scales far beyond human experience. A single orbit of Neptune takes about 165 Earth years. Pluto needs more than 240 years to complete a single journey around the Sun. These immense timeframes remind us that the universe moves patiently, without urgency. Nothing here rushes. Everything unfolds slowly, guided by forces that have remained consistent since the solar system formed. Closing reflections. As your thoughts rest among these distant worlds, it becomes easier to sense our place in the solar system. Earth is small, warm, and active, orbiting quietly within a much larger structure shaped by gravity and time. The outer solar system does not demand attention. It simply exists, steady and enduring, carrying the history of planetary formation in silence. This calm reminds us that not all mysteries need answers tonight. If this journey through the solar system helped you relax and unwind, consider liking this video and subscribing to the channel for more peaceful science stories designed to help you sleep. Rest well.